So good evening, everyone. This is lecture number 7 in diffraction, and this is a very small topic that we are going to cover, and we are going to cover it as quickly as possible. Talking about quickly, we are going to cover it in today's class only. So this is a small topic. You have to remember simple things about this topic, and if you remember these simple things, this topic is done. The first thing that we are going to understand about this topic is the meaning of the term diffraction. What do you mean by the term diffraction? Anyone? Any idea? What is the meaning of the term diffraction, Becha? What do you mean by the term diffraction? Diffraction means what? Diffraction means what? Anyone? No idea? Anyone? Yes. Try. What is the meaning of the term diffraction? It is the phenomena of, let me write the heading. I hope you can see this. Diffraction. The meaning of the term diffraction is the bending. It is the bending of light rays. It is the bending of light rays around the corners of any obstacle, or it undergoes, or it is moving through any aperture or a small opening. Whenever light encounters an obstacle, it bends, it moves around that obstacle. That phenomena is known as diffraction. To make you understand this, you can draw this if you want to. You can see this. If light encounters a small obstacle in this diagram number B that you see, there is a small obstacle here. When light encounters this small obstacle, you will see that you will see a shadow here and you will see light on the other side. That means light has bent. Similarly, if light encounters any opening, this is the opening that you see. It will again bend and spread out. This bending or spreading out of light rays when it encounters any obstacle is known as diffraction. Do we understand this? Yes or no? You want to draw this? You can draw this. I'll give you 2 minutes. Draw this. If you want to draw, if you don't, we will go ahead. Diffraction. This is a topic where you will be only asked the theoretical questions. Nothing much. Only theoretical questions you will be asked. If you note it down, please let me know.
Completed, sir.
Everyone completed?
Completed, sir.
Okay. Now, remember, this phenomena of diffraction is only observed. This phenomena is only observed, and that is an important point, if the size of the object or the opening D is nearly same as this D is the size of the obstacle or the opening is nearly same as the wavelength lambda of the wavelength. If they are nearly equal, both of them are nearly equal, then you have this phenomena of diffraction. Remember, this is a theoretical concept. Most of the questions are going to be of theoretical in nature. I hope you understand this. Yes or no? Most of the question will be theoretical in nature. Will you observe diffraction? They will give you certain wavelength of light and certain um, size of the obstacle, and then they will ask you whether you will observe diffraction or not. That time you'll have to remember, when do we observe diffraction? We observe diffraction only when the wavelength of the light is almost same as the size of the obstacle. They must be of the same order. If one is an Armstrong unit, the other one should also be in the Armstrong unit, and so on. Do we understand this? Yes or no? Please note this down. Once you are done, please let me know. I think you would have done this. Yes or no? Okay. Now remember, this diffraction pattern is a pattern which will be seen in all waves. Whether it's a light wave, whether it's a sound wave, it is a pattern. Diffraction is a phenomena that is seen in all types of wave. Do we understand this? Yes or no? Just note it down. Wave optics means everything about waves. Now, the next thing is, greater the greater wavelength means greater diffraction. Greater the degree of diffraction. Therefore, you see, and this is again a question, wavelength of the sound waves are more than the wavelength of light waves, and hence you can see the phenomena of diffraction very commonly in sound waves, but for light waves we have to make some special arrangements because the wavelength of light is very small. But for sound, you can easily see the phenomena of diffraction. If you are sitting in this room, even if all the doors are closed, there is a small opening, your sound can go on the other side. Do we understand this? But light from this room will not go on the other side easily. Yes or no? So this is the next point that you must remember. I hope everyone is noting them down. Yes or no? Both the classes? You're noting this down? Okay. Next is the minimum distance that you need to observe the phenomena. Minimum distance that the observer must be away to observe the phenomena. Again, this is a knowledge-based question. You just write the answer. D square by 4 lambda. This much distance you must be away if you want to observe the phenomena of diffraction. D is the size of the obstacle, and your lambda is the wavelength of light. I hope everyone is noting this down. Everyone noted this down.
That's
Okay. Then the next thing, there are two types of diffraction that we must know about. You must know their names. You must know what is the difference between them. and you will see them here, and you can draw this diagram because they can ask you a diagram. They can give you a diagram and they can ask you what are the two types of diffraction that are commonly seen. The first one is known as the Fresnel diffraction. The next one is known as the Fraunhofer diffraction. The difference between the two: in Fresnel diffraction, the source is here, and the screen is here. They are at a finite distance from each other. They are 5 meters, 6 meters, 8 meters, 9 meters, 1 meter, 2 meters. They are a finite distance from each other. In Fresnel diffraction, let me change the color of this so that looks same. Okay, but in case of the Fraunhofer diffraction, as you can see, ray of light is coming parallel. That means they are coming from infinity. That means there's infinite distance between the source and the screen. So you can draw these two diagrams to understand. In Fraunhofer diffraction, we use a lens to converge the light on the screen. So that is the difference between the Fresnel diffraction and Fraunhofer diffraction. I'll give you 2 minutes to draw the diagram and note it down. Have you noted it down, bacha? Please let me know if you're done. Take your time, don't worry. Shall we move ahead, bacha? Have you noted it down, bacha? Yes or no?
So 1 minute.
Okay, bachi. Take your time. You can see the screen now, bacha?
Done, sir.
Done, everyone? Boys? Okay. So what we were dealing is, okay, where is my screen gone? Okay. Fresnel diffraction and Fraunhofer diffraction, the two types of diffraction. Now, as soon as we understand the two types of diffraction, we can see how this diffraction happens, and this diffraction happens with a single slit. So you can write diffraction by a single slit. The heading is diffraction by a single slit. And as soon as you write the heading, you will draw this diagram. Oh, wrong color. This is diffraction by a single slit. And as soon as you see this diagram, you will be reminded of something that we have already done. Yes or no? This diagram looks like what? This diagram looks like the interference of that we had done in Young's double slit experiment. Yes or no?
Yes, sir.
The only difference is there we had two slits. The name of the slits were S1 and S2. Here we do not have two slits. We only have one slit which has a width of D. Then capital D is the distance between them. One wave is going from S1, so not slit. One wave is going from the top of the slit. The other wave is going from the bottom of the slit. And you have the path difference between the two waves as d sine theta. Do we understand this? This is the first thing that you have to see. Do we see this?
Yes, sir.
Draw this diagram. At the same time, also draw this one, which is the variation of intensity with the angle theta. And as you can see here, we see, okay, first I draw the diagram. I'll give you 2 minutes, then I will explain what is happening here. First, draw the diagrams. Let me know once you are done. I hope everyone is noting down.
Done, sir.
Everyone has noted this down? Okay, now see here, what do we see first thing? This entire thing is your central maxima. This entire thing is your central maxima. What you can note down here is the width of your central maxima. You can look from here. You can see this is the angular width, 2 lambda by d. So width of your central maxima is 2 capital D lambda by d, and the angular width, which we measure in terms of angular width theta, which is given here, angular width, the angular width is 2 times lambda by small d. Width of the central maxima is this much.
Sir.
Oops, you don't see it? Okay, sorry. You see it now? Width of the central maxima is 2 lambda by 2 capital D lambda by small d, and the angular width is 2 lambda by d. Central maxima has maximum intensity. Can you note this down? Central maxima has maximum intensity. This is the central maxima. Do we see the central maxima? Yes or no?
Yes, sir.
Central maxima has maximum intensity, and the width is 2 capital D lambda by small d, or 2 times lambda by small d. Notice down. Let me know if you have noted this down.
Done, sir.
Okay.
Done, sir.
Central maxima, as you can see, has maximum intensity. Now, look at the central maxima and look at these maximas. The other maximas are known as secondary maximas. The other maximas are known as secondary maximas. Do you see these secondary maximas? Now, the width of secondary maximas, width of these secondary maximas, and you can see the width of these secondary maximas here and here. The width of the secondary maxima is half the width of the central maxima. It is d lambda by small d. The angular width theta is lambda by d. So for secondary maximas, the width becomes half of the central maxima. Do we understand this? Yes or no? Have you noted this down? Please note it down. These are important points. Only these important points are going to come in your exam.
Done, sir.
Boys, you have done?
Done, sir. Done, sir.
Okay. The next point that we have to note down is on either side of central maxima, minima occurs. minima occurs on either side of central maxima. And for minima, the path difference delta x for minima is n lambda. The path difference is n lambda. This path difference is equal to d sine theta. This d sine theta is n lambda. So your sine theta, all these are same thing. Sine theta, which in the angle is small, it becomes equal to theta. It becomes n lambda by small d. This is how you can find out the location of the minimas. To locate the maximas, secondary maximas occur where your path difference delta x is 2n plus 1 lambda by 2. If you remember, the condition has been reversed here. In interference, where you having central minima, minimas, now you are having maximas. Where you having maximas, now you having minimas. The only thing that is same is at the center we are having a central maxima. Do we understand this? So d sine theta is 2n plus 1 lambda by 2. Or I can write your sine theta, which is approximately equal to your angle theta for small angles, will be equal to 2n plus 1 lambda by 2. This is the thing that you must remember about diffraction. Note it down, please.
Done, sir.
Completed, sir. Completed, sir.
Well done. Then this is a small summary of your difference between interference and diffraction. First, note them down. First, understand them. Then I'll give you enough time to note them down. Remember, this is the summary of your entire chapter in one column. So remember what we did about interference and diffraction. Interference, it results because of superposition of waves coming from two sources. There were two sources. Here, it is the superposition of wavelets coming from the same wavefront, only one wave. All fringes are of same width. All secondary fringes are of same width, but maxima is double. Do we get this? We have already noted this down. In interference, all fringes are of same intensity. In diffraction, intensity decreases. As you go away, intensity becomes less and less. Intensity of odd minimum may be 0. Here is not 0, definitely not 0. Then the position of the nth maxima and minima. Position of maxima is n lambda d by d. Here it is 2n plus 1. And they have forgotten to write 2, I guess. So you'll have to write 2. I will add 2 here. By 2d. The position of the dark fringes has been now taken up by the bright fringes and so on. Do we understand this? Path difference for maxima is n lambda. Here the path difference is 2n plus 1 lambda by 2. Minima was 2n minus 1. Lambda by 2. Again, they have missed the 2. Here it is n lambda. So maximas have been replaced by minimas. Minimas have been replaced by maxima. The only thing that is same is the central thing remains a minima. Do we understand this? Yes or no?
Yes, sir.
Note down this table. This table has everything that you need to know, both about interference as well as about diffraction in one table. So note it down, please. Note everything down, beta. Every point is a question. This is a very small topic and we are finished with this topic. So note them down carefully.
Sir,
Yes, beta?
sir, in simple, though became sir going.
Yes, beta?
Sir, in simple, though became sir washing clothes.
Okay, so you want to go?
Yes, sir. Again, though will go. Again, no washing clothes. Trouble.
Okay, go.
Thank you, sir.
Okay, note down. I hope you are noting it down, bacha. Okay, please let me know once you are done, so that you can go ahead with the class. It's almost done. We just need to solve 1 or 2 questions and we are done. So don't worry, we are done with this topic. Take your time, note them down, because this is the entire interference, YDSE, and diffraction in one table. I hope you understand this. Yes or no? Entire thing what we have done till now, this is in one table. The only thing that is not there is fringe width. Even fringe width is there. Yes. So everything is here. So if you can remember this table, you would be good to go.
Completed, sir.
Okay. So shall we move ahead then?
Yes, sir.
Okay. Now remember, we have done this single slit diffraction. Now what can happen is, sometimes in place of this single slit from Fresnel diffraction, they may give you Fraunhofer diffraction. Now what do I mean when I say Fraunhofer diffraction? Is that they can give you this lens. They can give the diagram instead of this slit wala diagram which we are doing now. They can give you this lens wala diagram. Now if they give you this lens wala diagram, right now what we know and what we have derived is the width of the central maxima and everything in terms of capital D. Yes or no? Capital D is the distance between the screen and the slate. Yes or no? Now, if they give you this convex lens, that means they have given you the Fraunhofer diffraction. If they give you the Fraunhofer diffraction, what do you do? How do you get the answer for Fraunhofer diffraction? So remember this. In the formula for the slate, you just replace this D, oops, wrong color. This replace D by F for Fraunhofer, where F is the focal length of the lens. So now you can write this formula for Fraunhofer diffraction as an important point. For Fraunhofer diffraction, the width of the central maxima becomes 2 times lambda F by D. The angular width becomes 2 times lambda by D. So what has happened is, this capital D has been replaced by F. What is this F, bacha? What is this F? What is this F? Huh? Just written F, just for the sake of writing it. What is this F?
Focal length.
Of what? Focal length of the lens that we had seen. Just now I had shown you the lens. F is the focal length of the lens. So basically what it means is, this is the distance between the source and the screen. Effectively, this F is the distance between the source and the screen. Do we understand this, bacha?
Yes, sir.
So remember, if they give you for Fraunhofer diffraction 2 times lambda into F by D would be your answer. I hope everyone has understood this. Yes or no? No, yes.
Yes, sir.
Okay, that takes us. We've done this thing. So what we'll do now is to solve a couple of questions, and then we can rest our case here. So are we ready for the questions? Never. Done this, done this. Okay. Where is the question? I have seen the question. Yes, here is the question. So take your time and give me the answer for this one. This is question number 1 and it comes on your screen now. Question number 1. When wave of wavelength 0.2 centimeters is made to incident normally on a slit of width 0.004 meter, then the semi-angular width. What do you mean by semi-angular width? Angular width is theta. Theta by 2 becomes semi-angular width. Do you understand this? So this is I wanted you to understand. Theta by 2 is your semi-angular width. Do you understand this?
Yes, sir.
Please note it down. That is the reason this question was done. Semi-angular width is theta by 2 of the central maxima. I will give you 2 minutes to solve this. Yes, bacha, do we have any answer? Or you need more time?
So 30 degrees.
30 degrees is correct. Absolutely correct. 30 degrees. How did you get 30 degrees? It is very simple. So your theta is, or I should say, if the angle is big, the value of sine theta. Do you understand this? The value of sine theta is, for small angle, it is theta. The angle is big, it is going to be sine theta. Sine theta is 2 times lambda by d, right? So your theta is the half of the angle. So it will be half of this. So sine inverse of lambda by d. This is how we calculate it. When you put the values, you will get theta as sine inverse of half. So theta becomes your 30 degrees. Okay, we got this?
Yes.
Okay, then we can do this problem. One more. A parallel beam of monochromatic light is incident on a narrow rectangular slit of 1 mm width. Diffraction pattern is seen on a screen at a distance of 2 meters. The width of the central maxima is found to be 1.5 mm. What is the wavelength of the light that is used? I'll give you 2 minutes to do this. Shall I do it, bacha? Now it's to be done. The width of the principal maxima is given. Yes or no? Beta, the width of the central maxima is given. 2 times lambda d by small d. Yes or no?
Yes, sir.
That is given. That is given as how much, bacha? 1.5 mm. So 1.5 into 10 raised to the power minus 3. So how will I get the value of lambda? 1.5 into 10 raised to the power minus 3 multiplied by d. D is 1 into 10 raised to the power of minus 3, 1 mm, divided by 2 into the distance between the slit and the screen, that is 2 meters. That is the answer, my dear friends, that you should get. Did I do it correctly or not? Are you getting something different? Okay, the answer might be different because they have done it. They have given the wrong option. What is the answer that you are getting, beta? You did it in the same way? Yes or no? Okay, the answer that they have given, they have taken it as 2.5 and then they have found out the answer. So if I put this as 2.5, let us see if you get the answer. Let me make it as 2.5. They've given the answer using 2.5. They have calculated the answer using 2.5. So I think from there you will get the answer as 6250. Are you getting 6250 now? So that is the answer, beta 6250. Yes or no? Okay. So here it is. As you can see, there are only two formulas that you have to remember. The width of the center maxima is the only thing they are going to ask ever in any exam. If you remember that 2 times lambda capital D by small d, you are done. So with this, we come to the end of this chapter. This part, diffraction, in the next class. Tomorrow, we will be dealing with polarization. Similar small topic, but one question can come from this. So tomorrow's class and today's class, out of these two, one question can definitely come, will definitely come in your exam. So these two classes will account for +4 or maybe +8. And these questions, as you can see, are very simple. So we'll meet in the next class. We'll do polarization. One question for polarization is supposed to come. So we'll cover it in the next class. If you have any questions, ask, else we call it a day. Take care. Have a nice day.